Welcome to this model. On this model, let's have an insight of quality of service. Quality of service is an internet networking issue that has been discussed more than 5 decades, and we can informally define the quality of service as something a flow seek to attain. And Traditionally, four types of characteristics are attributed to flow: reliability, delay, jitter, and bandwidth. Let's see one by one. Reliability is a characteristics that a flow needs. Lack of reliability means losing a packet or acknowledgement, and which entails a retransmission. However, the sensitivity of the application programs to reliability is not the same. For example, it is more important that electronic mail, file transfer, and internet access have been reliable transmissions than telephony and audio conferencing. Delay is nothing but source to destination delay is another flow characteristics. Again, applications can tolerate delay in different degrees. In this case, telephony, audio conferencing, video conferencing, and remote login need minimum delay, while delay in file transfer or email is less important. And the third category is jitter. Jitter is a variation in delay for packets belonging to the same flow. For example, if 4 packets depart at times 0, 1, 2, 3 and arrive at 20, 21, 22, 23, all have the same delay, 20 units of time, right? On the other hand, if the above 4 packets arrive at 21, 23, 21 and 28, they will have different delays at 21, 22, 19 and 24. So for applications such as audio and video, the first case is completely acceptable and the second case is not. For these applications, it doesn't matter if the packets arrive with a short or long delay as long as the delay is same for all packets. So for this application, the second case is not acceptable at all. Jitter is defined as the variation in the packet delay. High jitter means the difference between delays is large. Low jitter means the variation is small. Now let's see how multimedia communication deals with jitter, and if the jitter is high, some actions is needed in order to use the received data. And the third characteristics is bandwidth. Different applications need different bandwidth. In video conferencing, we need to send millions of bits of data to refresh a color screen, while the total number of bits in an email may not reach even a million. So based on the flow characteristics, we can classify flows into two groups, with each group having similar levels of characteristics. The categorization is not formal or universal. Some protocols such as ATM have defined classes, as we'll see later. And now let's discuss about some of the techniques to improve the QoS, that is quality of service. So now we have defined the QoS in terms of its characteristics. Now let's see some techniques which can be used to improve the quality of service. And there are common methods called scheduling, traffic shaping, admission control, and resource reservations. These are some of the techniques which are used to improve the quality of service. Let's see one by one. First is scheduling. Packets from different flows arrive at a switch or router for processing. So a good scheduling technique treats the different flows in a fair and appropriate manner. Several scheduling techniques are assigned to improve the quality of service. Now let's see the three of them. First is Fifo queuing, second is priority queuing, and third one is weighted fair queuing. In Fifo queuing, that is first in first out queuing, packets wait in a buffer queue until the node, router or switch is ready to process them. So if the average arrival rate is higher than the average processing rate, the queue will fill up, the new packets will be discarded. A Fifo queue is familiar to those who have had to wait for a bus at bus stop. And in priority queuing, packets are first assigned to a priority class. Each priority class has its own queue. The packets in the highest priority queue are processed first. Packets in the lowest priority queue are processed last. You can notice that the system doesn't stop serving a queue until it is empty. And we can see the priority queuing with two priority levels for simplicity. A priority queue can provide better QoS than FIFO queue because higher priority traffic such as multimedia can reach the destination with less delay. However, there is a potential drawback if there is a continuous flow in the highest priority queue. A packet in the lowest priority queues will never have a chance to be processed. This condition is called as starvation. And a better scheduling method is weighted for queuing. So in this technique, the packets are still assigned to different classes and admitted to different queues. The queues, however, are weighted based on the priority of the queues. Higher priority means a higher weight. The system processes packets in each queue in a round-robin fashion with the number of packets selected from each queue based on the corresponding weight. For example, if the weights are 3, 2 and 1, 3 packets are processed from the first queue, 2 from second queue and 1 from third queue. If the system doesn't impose priority on the classes, all weights are equal. So in this way, we have fair queuing with the priority. And now let's see the technique with the 3 classes. One is traffic shaping. Traffic shaping is a mechanism to control the amount and rate of the traffic sent to the network. And 2 techniques can shape the traffic. One is leaky bucket and the other is token bucket. First, let's see about leaky bucket. If a bucket has a small hole at the bottom, the water leaks from the bucket at a constant rate as long as there is water in the bucket, right? So, the rate at which the water leaks doesn't depend upon the rate at which the water is input to the bucket unless the bucket is empty. The input rate can vary, but the output rate remains constant. Similarly, in networking, a technique called leaky bucket can smooth our bursty traffic. Bursty chunks are stored in the bucket and sends out at an average rate. You can see the leaky bucket and its effects. So, if we assume that the network has committed a bandwidth of 3 Mbps for a host, the use of a leaky bucket shapes the input traffic to make it conform to this commitment. The host sends a burst of data at a rate of 12 Mbps for 2 seconds and a total of 24 megabits per of data. The host is silent for 5 seconds and then sends the data at a rate of 2 Mbps for 3 seconds and for a total of 3 megabits of data. So in all, the host has sent 30 megabits of data in 10 seconds. So the leaky bucket smooths the traffic by sending out data at a rate of 3 Mbps during the same 10 seconds. Without the leaky bucket, the beginning burst may have hurt the network and by consuming more bandwidth than is set aside for the host. So we can also see that the leaky bucket may prevent congestion. As an analogy, consider the freeway during the rush hour, that is bursty traffic. So if instead commuters could stagger their working hours, congestion on our freeways could be avoided. And FIFO queue can hold the packets if the traffic consists of fixed size packets, that is cells in ATM networks. The process removes a fixed number of packets from the queue at each tick of the clock. If the traffic consists of variable length packets, the fixed output rate must be based on the number of bytes or bits. So there is an algorithm for variable length packets. First, we have to initialize the counter to n at the tick of the clock. If n is greater than the size of the packet, send the packet and decrement the counter by the packet size. So we have to repeat this step until n is smaller than the packet size. So we have to reset the counter and we have to go back to step 1. So a leaky bucket algorithm shapes bursty traffic into fixed rate traffic by averaging the data rate. It may drop the packets if the bucket is full. And the next category is token bucket. The leaky bucket is very restrictive. It doesn't credit an idle host. For example, if a host is not sending for a while, the bucket is empty. Now, if the host has bursty data, the leaky bucket allows only an average rate. The time when the host was idle is not taken into account. On the other hand, token bucket algorithm allows an idle host to accumulate credit for the future in the form of tokens. For each tick of the clock, the system sends n tokens to the bucket. The system removes one token for every cell of or byte of data sent. For example, if n is 100 and the host is idle for 100 ticks, the bus collects 10,000 tokens. Now, the host can assume that all these tokens in one tick with 10,000 cells, or the host takes the 1,000 ticks with 10 cells per tick. So, in other words, the host can send bursty data as long as the bucket is not empty. So the token bucket can easily be implemented with a counter. The token is initialized to 0 each time a token is added. The counter is incremented by 1 each time the unit of data is sent. The counter is decremented by 1. When the counter is 0, the host cannot send data. So we can also combine token bucket and leaky bucket. And by combining these two techniques to credit the idle host at the same time to regulate the traffic, the leaky bucket is applied after the token bucket. The rate of leaky bucket needs to be higher than the rate of tokens dropped in the bucket. So a flow of data needs resources such as buffer, bandwidth, CPU time, and so on. The quality of size is improved if these resources are reserved beforehand. So we can say that quality of service model called integrated service, which depends heavily on resource reservation to improve the quality of service. And the fourth technique to improve the quality of service is to use the admission control. Admission control refers to the mechanism used by the router or a switch to accept or reject a flow based on predefined parameters called flow specifications. Before a router accepts a flow for processing, it checks for the flow specifications to see if its capacity in terms of bandwidth, buffer size, and CPU speed, and its previous commitments to other flows can handle the new flow. Thank you.